So, welcome back to lectures on engineering mathematics 2, and this is lecture number 29, and we will continue our discussion on polynomial interpolation. So, in this lecture we will be talking about two different techniques, two different methods for getting interpolating polynomial. So, the one is Newton's divided difference, which is quite similar to what we have done Newton's forward and backward interpolation formulas, and the other one we will be talking about the Lagrange interpolation formula, and these both are for unequal intervals. So, the grid points or the nodal points are not just equidistant in this case. So far we have discussed in previous lectures the Newton's forward interpolation formula, where the formula looks like this one, where we have somewhere there in each term this h, which was the distance between the nodal points x naught, x 1 or x 1, x 2, and it was assumed that they are equidistant. Similarly, for the Newton's backward formula as well, we have assumed that these nodal points are equidistant. So, this is a note here also, that in both the formulas were derived taking equidistant nodal points, and now we will be talking about two more formulations which are more general in the sense that we can have non equidistant nodal points as well. So, the first one is the Newton's divided difference formula, which is very similar to what we have already done. So, let us go back to what we have started with for the derivation of Newton's forward or the backward difference formula. So, given that we have 2 points x naught and x 1, and their corresponding values f x naught and f x 1 are given. So, basically 2 points are given, and as we know that we can fit a straight line which will pass through these 2 points. So, we take this linear polynomial as b naught and b 1 x minus x naught, as usual we have taken earlier also. For the sake of simplicity of the evaluation of these coefficients, we have taken this special format, and immediately when we substitute x is equal to x naught. So, this polynomial has to give the value f x naught and equal to b naught, and this term will be 0. So, the b naught we will get as f x naught, and then we can go for the other point, which is x 1. So, at the point x is equal to x 1, when we substitute, we will get f x 1 is equal to b naught plus this b 1 and x 1 minus x naught. So, from here we can get b 1 as usual we have done before, and the b 1 will be f x 1 minus f x 0 over x 1 minus x naught. And earlier we have written this b 1 in terms of the forward difference formula, assuming that they are equidistant, and this x 1 minus x naught was taken as h. So, now to make it more general, this expression here, which is f x 1 minus this f x naught over x 1 minus x naught, we are defining this as f x 1 x naught with the symbol, which is called the divided difference formula. So, this is the divided difference, taking these x 1 and x naught two nodal points. We are defining this ratio by this symbol f x 1 x naught with the square bracket. So, this is what we call the divided difference. So, having this b 1 in terms of this f x 1 x naught, we got the polynomial as f x naught plus this divided difference here with 2 points, and then we have here x minus x naught, which was there already in the polynomial. So, the b 1 we have substituted as this divided difference, and the b naught was f x naught. So, we got this polynomial of degree 1 in terms of the divided difference. Similarly, we can continue for the quadratic polynomial as well, and in this case we need 3 points. So, x naught, x 1 and x 2, and corresponding values f x naught, f x 1 and f x 2. So, in this case naturally we can fit a polynomial of degree 2, and again we will take this structure b naught b 1 x minus x naught and b 2 x minus x naught x minus x 1. and we will again go for the evaluation of these unknown, these coefficients, that is B naught, B 1 and B 2. So, for B naught, when we substitute x is equal to x naught, we will get immediately B naught, and similarly B 1, which we have already evaluated before, it will be the same value. So, f x 1 x naught, and then substituting x is equal to x 2, we can also get B 2. So, B 2 will have this format, and these two expressions here we can again write in terms of the divided difference, which we have already defined for 2 points earlier. That means, the first one is f square bracket x 2 x 1, and the second one is the divided difference, which is denoted by f and the square bracket x 1 x naught, and divided by this x 2 minus x naught. So, here we have another this divided difference of this higher order, which we can denote, because this is again the difference of those divided difference which we have computed first and then divided with this the maximum difference between these nodal points we have. So, x 2 was the highest value and x 1 the minimum value. So, that difference is coming in the denominator. So, here this ratio we are defining as this divided difference again with these 3 points, that is x 2, x 1 and x naught. So, having this B 1 in terms of this divided difference, B 2 also in terms of this divided difference, we can now write down the polynomial, which is second degree polynomial now. So, f x naught, then f x 1 x naught, this divided difference multiplied by x minus x naught, and then we have this another divided difference and multiplied by this product x minus x naught and x minus x 1. So, now we can continue this for the third order polynomial or the fourth order polynomial, and in general we have such a formulation. See, nth degree polynomial for given n plus 1 points, we have f x naught, this is the divided difference taking x 1 and x naught. Here again we have the 3 points and so on, we have here n plus 1 points and the corresponding products. So, this is the formula which is more general than for instance the Newton's forward difference formula, and this can be used when we have non equidistant nodal points given in our data, and the formula looks much simpler than the divided difference, because in this divided difference already that h I mean the distance between the nodal points are hidden. So, we have much simplified formula in terms of this, and the interesting point is that these divided difference again we can get with the help of table, as we got the differences, the differences backward and the forward. Here also these divided difference we can directly obtain from the table and substitute here, and we can get the desired polynomial. Well, so this formula is called Newton's divided difference interpolating polynomial. Now, coming to the other one which we will also discuss in this lecture, that is the Lagrange interpolation formula. So, in this case again we will go back to the what we are doing with the linear polynomial, for instance. So, taking 2 points x naught f x naught and x 1 f x 1, what we have just seen, we have seen this divided difference formula. So, the polynomial of degree 1 was f x naught, and this first order is divided difference, and then we have x minus x naught, or if we substitute here this divided difference. So, that was actually this f x 1 minus f x naught over x 1 minus x naught. So, having this polynomial of degree 1 which passes through these 2 points, and now what we are doing, we are just rewriting this, and that will be another format which is called the Lagrange interpolating polynomial. Well, so we have written now f x naught, we have taken common, because f x naught appears here also and f x naught is there, and then we have f x 1 which will just appear with x minus x naught over x 1 minus x naught, and with the f x naught this expression will come x minus x 1 over x naught minus x 1. So, we have rewritten this polynomial of degree 1 in this form, where we have some polynomial here, the value of the function, again this polynomial of degree 1 and then f x 1. So, these polynomials here, for example, this first one, this is called L0x or the Lagrange polynomial, and this is the Lagrange polynomial L1. So, this 0 means we have x naught here minus the other points here. L1 means we have subtraction here with x1 minus. So, we will generalize this in the next slide and then it will be more clear. So, these L0 and L1 are called polynomials of degree 1 because these are degree 1 polynomial. We have only x there and we have only x there. So, having this format, what is the beauty now that we can write down in the form of a sum, that this P1 here is I goes from 0 to 1, and we have this so called the Lagrange polynomial of degree 1, and then we have f x I, the value of the function at x I. So, these Lagrange polynomial of degree 1, we can define Lagrange polynomial of degree 2, degree 3, etc., and depending on the given number of points we can generalize this formula. In this case we have only 2 points there. So, these Lagrange polynomial of degree 1 are appearing here LIX, but when we have for instance 3 points, those polynomials will be of degree 2 polynomial. Again the same structure of the formula will continue. So, for the linear case we have seen that the P1x can be written in this summation format, and then we have L0 and the L1 written in this form. Indeed, these L1 L0 we can write in a more compact form or more general form, that Li is nothing but this product here, because when we derive the second order we can see the structure easily. So, we are avoiding here just to save some time, and here we have just the product. So, this term here and then keep on doing this product, but in this case since this is going from j 0 to 1 and then we have j not equal to I. So, when we are talking about L0, so j will not be 0, j will be just 1, and we have x minus x1 and this I is 0. So, x minus x1, only this, there is no product there, and similarly with L1 we will get this expression. So, this is more general, but when we are talking about the second order polynomial or third order polynomial, then this product will come, such terms will come in product to make this second order or the third order polynomial. Well, so the generalized Lagrange interpolating polynomial, suppose there are n points are given x0 f x0 or n plus 1. So, x1 f x1 and so on xn f xn. So, there are n plus 1 data points are given, then we can construct a polynomial of degree n. That means, now generalizing just this polynomial which we have just done for degree 1, but we can do for 2 and then generalization will be much easier. So, here this P n, that was just 1 there. So, we have n there, and therefore, this n will come here too. I goes from 0 to n LIX and FXI, because there are this FXIs are also n plus 1 in number. So, all FXI will come here, and these are the Lagrange polynomial of degree n now, because n plus 1 points are given. So, these Lagrange polynomial are defined exactly what we have done for this one, that j not equal to I and j goes from 0 to n, and then such term will be multiplied. So, for instance, this one if we write in the expanded form, so for ith, so if we are talking about Li, there will be a missing term here, because we are doing with xi. So, xi minus x naught, xi minus x1, xi minus xi minus 1, and naturally xi minus xi will not come, otherwise this does not make any sense. So, except that I from this xi, all other points will be subtracted in the denominator. That is what it is easy to remember. So, the first let me just write down this denominator from this. If we are talking about the ith this polynomial, then we have xi everywhere, and all other points other than xi has to be subtracted there. And now, we go to the numerator, this xi will be just replaced by x everywhere, and the rest everything will remain the same. So, this is what we can easily remember, these Lagrange polynomials of degree n indeed. So, these are called the Lagrange polynomials of degree n. So, it is a very simple formula to remember. We have just LIX FXI, that is the formulation here, and we know already these are the standard results, that what are the Lagrange polynomials of degree n. So, now we can go to the numerical example. So, the first we are taking here that using Lagrange and the Newton's divided difference formula, construct a polynomial of degree 2 or less with the following data. So, we have the 3 data points. So, we can expect a polynomial of degree 2 or less in some cases. The value of f is also given here 1, 3 and 3. So, first let us go through the Lagrange interpolating polynomial. So, here we have 3 data points. So, we will get Lagrange polynomial of degree 2. So, polynomial can be written again this LIFXI and L naught. Now, here we note L naught, L 1 and L 2. So, L naught will be x naught, x naught. So, x naught minus x 1, x naught minus x 2, and this x naught we will replace by this x in both the places, and that will become the numerator. So, we have x minus x 1, x minus x 2, x naught minus x 1 and x naught minus x 2. So, x minus x 1 is, so this is x naught, the first one, this is x 1 and this is x 2. So, x minus x 1, that is 2, x minus x 2, that is 4 there. Then we have x naught, that is 1 minus x 1, that is 2, and here we have x naught minus x 2, that is 1 minus 4. So, this Lagrange interpolation, the Lagrange polynomials of degree this 2, the L 0 we have x minus 2, x minus 4 by 3. Similarly, for L 1 we can compute again. So, here the only difference is now we have x 1 and then all other points will be subtracted. So, first we have x 1 minus x naught, then we have x 1 minus this x 2, and then we have in the numerator this x 1 will be replaced by the x there, and we have the formula. So, again putting all these values of x naught and x 1, x 2, we can get the second order polynomial, this L 1, and then we have the L 2 there. For L 2 we have to have here x 2, x 2. So, x 2 minus x 0, x 2 minus x 1, all other points will be subtracted, and then we have there x 2 will be replaced by this x 1. So, we have x minus x naught and x minus x 1. So, putting all these values of x naught and x 1, we will get this second order polynomial, second degree polynomial, which is written here 1 by 6 x minus 1 and x minus 2. So, having these all desired polynomials of degree 2, L 0, L 1 and L 2, we can now write down this Lagrange polynomial. Only thing we have to multiply it just by the function value to each of these L's. So, here we have this first L naught multiplied by this value of f x naught, this was 1, then we have this L 1 there and the value at this x 1 point which was 3, and then again here it was 3. So, this is L 2. So, when we can simplify this and we get minus 2 by 3 x square plus 4 x minus 7 by 3. So, that was using Lagrange interpolation formula. Now, coming to the Newton's divided difference formula, we have to construct the difference table to use this formula. So, first we will get this divided difference table. So, we will write down in the first column as x. So, 1, 2 and 4. In the f x we have 1, 3 and 3, and then the first this divided difference, how do we get, is exactly similar to getting these finite differences which we were doing in Newton's forward and backward difference formula. Just subtract this one here. So, 3 minus 1, that is 2, and we have to also divide by the corresponding values of x, that is 2 minus 1, 1. So, 3 minus 1, 2, divide by 1, that is 2 here, and in this case 3 minus 3, that is 0, and then 4 minus 2, that is 2. So, 0 by 2, that is 0 again. So, we have this. Now, in the last one we have to subtract this 0 minus 2, that is minus 2, and then we have to subtract 4 minus 1. So, this is nothing but this 2 minus 0 sorry 0 minus 2. So, 0 minus 2 and divided by this 4 minus 1, 4 minus 1. So, we have minus 2 by 3. So, that is the value here for this divided difference having these 3 points. And then we can use simply in this formula where we have f x naught, then this divided difference x minus x naught, divided difference x minus x naught. So, in this case we can substitute now these divided difference. One more benefit here similar to what we have for Newton's forward and backward difference formula. If you want to add one more point, for instance, then one extra term will be coming in this formulation, but the rest all the calculation will remain as it is, and we can continue just having one more term there, and we will get a new polynomial. Whereas, in this Lagrange interpolation formula, what we have to compute again all these Lagrange's interpolating polynomials, the Lagrange polynomials, because the degree of the Lagrange polynomial will change. So, there will be again fresh calculations, but here in this case if you want to add one more point here, the table has to be updated, and then just one extra term will be appearing besides this existing one. So, here again we when we substitute these finite differences, so we will get the result which is naturally the same polynomial which we have just derived using Lagrange interpolation. One more example, that is the last example now in this lecture. So, we use the Lagrange and the Newton's divided difference formula to derive interpolating polynomial again from this following table. So, now we have more data. So, we have 6 points 0, 1, 2 and the 4, 5, 6, they are also not equidistant, and then corresponding values are given. So, in this case we will go first with the Newton's divided difference formula, and we will realize indeed when we have this much data, and in particular in this example we will see that the Newton's divided difference formula, it is much easier to derive this interpolating polynomial, whereas in the Lagrange interpolating formula is much more complicated. So, coming to the divided difference table, we have to write all the values of these x here 0, 1, 2, 4, 5 and 6, and then the corresponding value of f, which are 1, 14, 15, 5, 6 and 19. And then we have to construct this divided difference table as we have done before. So, this 14 minus 1, that is 13 and divided by 1. So, this will be 13 here, again 15 minus 14, that is 1, and 2 minus 1, 1. So, division with 1. So, we have 1. Then 5 minus 15, that is minus 10, and then we will divide by this 2. So, we will get minus 5, that is true here. Then we will get 6 minus 5, 1, and so 1 divided by 1, 1. Then we get 19 and minus 6, 19 minus 6 divided by this 5 minus 6, that is 1. So, we have 13 which is there. So, similarly we have to continue with this process. For this case, now we have to make this difference 1 minus 12. So, 1 minus 13. So, will be minus 12, and then we have to divide now with 2 minus 0. So, this will be 1 minus 13 and divided by this 2 minus 0, because now the difference here 3 points will be coming together. So, this is minus 12 and then 2. So, it is minus 6 there. So, here we have minus 6, and then similarly we have 5 minus 1, minus 5 minus 1. So, minus 6, and then we have here 2. So, minus 6 minus 5 minus 1. So, minus 6 and divided by 3 there, 4 minus 1 3. So, we will get minus 2. So, and so on, we have to continue this, it will be 2, and then we will have a 6 there. And further we have to go with this next difference. So, here will be like minus 2 and minus 6. So, there will be 6 there, and divided by, now we have to have a difference of these 4 points. So, here 4 minus 0. So, that will be 4. So, here 6 minus 2, that is 4, and divide by 4. So, we will be having 1 there. So, we have 1, and interesting here is that when we do here also we have 2 minus 2, that is 4, and from here also we will getting 4. So, 4 divided by 4 again 1, here also we will get 1. So, all are 1 1 1, and once we get such a situation, rest all going to be 0. So, we have 0 there and we have 0 there. So, this is the finite difference table we have. Having this finite difference table, we can now go for the formula, the divided difference formula, which has here f x naught, we have f x 1 x naught, then here and then and so on. We are not writing now this further, because these are going to be 0. So, though we are expecting when 6 points are given the 5th degree polynomial, but in this case we will not get, we will get only the third degree polynomial. So, here substituting all these values. So, this f x 1 x naught is 13, then we have these 3 points. So, we have minus 6, when we have these 4 points, this is 1, and these are zeros. So, 2 more terms will come, but they will become 0. So, we are not writing them. And now, it is much simpler to work with. So, we got this third degree polynomial. So, what is our observation on these divided difference formula, that once the table is ready, and now for instance in this case we got these zeros at 2 places there. So, there was no higher order terms coming automatically, and we have less calculation, and finally, we got this third degree polynomial easily. Whereas, if we want to go with the Lagrange interpolation formula, what will happen? Given the data, we have to now compute all L1, L0, L1, L2, L3, L4 and L5, and then only after combining all these with a lot of calculations we will get again this third degree polynomial, but here the calculations will be more, because we have to compute these 6 terms. So, this is the first term, we have this L0 here 5 degree polynomial multiplied by this value f x 0. Then we have to have this again L1, the 5 degree polynomial, then will be multiplied by this 14, we have again 5 degree polynomial multiplied by 15, and then here again 5 degree polynomial, which will be multiplied by 5, this will be multiplied by 6 here, and then it will be multiplied by 9. So, we have to now simplify all these here, each having 5 degree polynomial, and there will be cancellation of degree 5 terms, degree 4 terms, and finally, we will get the polynomial which is just third degree polynomial. But what is the difference between these finite difference divided difference formula and this one, that here we have to do lot of calculations, because each Lagrange polynomial is a 5th degree polynomial, and that has to be simplified to have this lower degree polynomial, which is the case here. So, in many cases this Lagrange interpolation usually when it is a higher order data is given and more points are given. So, this Lagrange interpolation formula becomes really tedious, whereas for instance, in this case where there was a simplification, the finite differences terms become 0. So, the evaluation of the lower degree polynomial was easier in the finite difference formula. Well, so these are the references used for preparing this lecture, and just to conclude again, so we have discussed 2 formats here for computing the interpolating polynomial. One was the Newton's divided difference formula, where we have to just compute these divided differences usually from the table, and then we can get this polynomial. Whereas, in the Lagrange interpolation formula, it is slightly different. We have to compute the Lagrange polynomial L0, L1, L2 and so on, multiplied by this f x I. And in the last example, we have seen that using this Newton's divided difference formula, it was much easier to compute the polynomial, which was actually lower degree polynomial, though more values were given there, and whereas in the Lagrange interpolation formula we have to compute all the Lagrange polynomials, and then we have to combine in this formula, and the calculations were really tedious. Well, so that is all for this lecture, and I thank you for your attention.